Euclidean Geometry, Ratio and Proportion, Similar Triangles, Part 1. Now, you should have dealt with similar triangles in the past, of course, in your previous geometry career, usually involving two triangles with equal angles. So let's have a look. If two triangles are equiangular, so notice it's actually this triangle is just this one increased in size. It could be in any position we like, but we've kept it the same there just to avoid confusion. And we have equal angles, equal angles, equal angles. Then their corresponding sides are in proportion. And what we mean by that is A over P, side one over side other, the corresponding side of the other, equals side 1 over side and the other equals side 1 over side and the other. So there we are. And this is proven using proportional in-step theorem. The proof is in the video series. Which means triangle ABC is similar to triangle PQR, and that follows AB over PQ equals BC over QR equals AC over PR. Order is very important. So if we have angle A equals angle P, then notice they're both first in the statement. B equals Q, so they're second in the statement, and C equals R, so they are third in the statement. And that sums up a whole lot about sides as well. If you have a look now, AB over PQ, first second over first second, equals BC, second third, over QR, second third, and first third over first third. So now, to prove triangles similar, it's the same procedure as proving triangles congruent. In triangles, this and this, three facts, therefore triangle this similar to triangle that. We always give the case for congruency, so we must give the case for similarity. In those cases, angle, angle, angle. You can prove two triangles similar using proportion, but we won't do that in this course. And notice that the third one can always be angle sum triangle, the third one here, because if we have two pairs of angles equal between two triangles, the third pair must be equal. So that makes similar triangle proofs a little bit easier. So let's do a proof. Prove that triangle KLM is similar to triangle KZY. And we're going to start with the triangles KLM, KZY. So what you could do is say, well, there's an angle in the one triangle, Y. What would it probably be equal to the other one? M. Can we see a reason why? There's an angle, Z in the one. There's the angle it's equal to the other. Aha. So we can use that part of the proof. K is the angle in one. K is the angle in the other. And they're exactly the same angle. They're not vertically opposite. They are common. So therefore, K is common. We start with that. And this is perpendicular to this, and that's perpendicular to that, so we have those both equal to 90 degrees. KLM equals Z equals 90 degrees given. Notice I didn't just put KLM equals Z. Nowhere there does it say KLM equals Z, but it does say that those are both perpendicular, therefore we have them both 90. And of course, angle sum triangle. Therefore, KLM similar to KZY. Now, don't ever look at the statements here. They do give it the correct order, but just in case, angle K common, so KK. L was equal to Z, so LZ, and then MY, MY. Now, prove that KL times KY equals KM times KZ. There are equal angles in the correct order, meaning that KL of KZ first second, LM over ZY, second, third, and first, third, first, third. And we can go straight to there from the similarity statement. And that gives us what we want to prove. Thought strategy. Let's do an example to give you a thought strategy. So there we are. We have perpendicular, perpendicular. Prove that AB squared equals AD times DC. Now, the one thought strategy is to say, well, if it's AB squared, then AB must be involved in both triangles. If it's BD squared, BD must be involved in both triangles. That's quite useful. But have a look at this thought strategy too. I take AB squared equals AD times AC, and I say, well, that means AB times AB equals AD times AC. Now, watch my little swap here. Notice I do an algebraic move to move one of these below, one of those below. There we are, like that. And it doesn't matter which way around I've done it. It really doesn't. Now, what I'm going to do in my thought strategy is I'm going to do what I call the vertical horizontal test. I'm going to go vertically through there and see what letters I pick up, and vertically through there to see what letters I pick up. And I'm going to say, does that give us triangles? If not, then I go horizontally. Let's go vertically through that there. ABC, ADB. Now, what I ask is, do these look similar? I think they could. That's got a right angle there. This big red one, the red shaded, has a right angle. And they have a common angle. Yes. A common, D1 and B both equal 90 degrees. If not, if we weren't successful, then we try the horizontal. We'd go that way and that way. In this case, it gives us the same triangles, often the case. But sometimes it gives you 4 different letters or a straight line, which could mean proportional intercept theorem. So keep a watch on that, be sharp on that. And if you find that horizontal or vertical doesn't work and you try the other one and you get 4 letters and then a straight line as your 2 options, it is probably proportional intercept theorem, not similar triangles. So let's do the proof. We already know we're doing the green and the red triangles. 1, A is common. 2, D1 equals B equals 90 degrees. Notice when I say B, I mean the whole of angle B. And then the final angle B1 in the green is equal to the final one in the red C. And therefore, ABD, triangle ABD equals triangle ACB, angle, angle, angle. Now I want AB squared out of it. To get AB squared, I'm going to have an AB above and an AB below. AB from this triangle and AB from that triangle. That's what I want, and that's what I'll write very first. I'll say, well, there we are, because that'll give me my AB squared, and I can get it from those triangles. Notice that I put similar triangles proven. Some educational authorities are very fussy about you having to put that there. Seems to be a bit painful because you've just done it. But if you really want to make sure you don't lose marks, then just put similar triangles proven there. Now we say, well, AB from the green triangle, what must go below? First, second, if we need first, second there. And that's why we get AC. Now, AB from the second triangle is first, third. So therefore we need first, third from the green, and there's AD. Algebraically, that gives us exactly what we wanted to prove. Phew. Now, thought process for the second one, we're going to do the same thing. BD squared, BD times BD. I'm getting right as fractions. Doesn't matter. I brought AD below, but you could have taken DC below instead. It really doesn't matter because you're going to do a vertical and a horizontal. Vertically, we get BDA and DCB, and they look quite feasible, the green and the red triangles. So therefore, 1, B1 equals C. Proven. There we are. 2, D1 equals D2 equals 90 degrees, and that's given. It's given that BD is perpendicular to AC. And 3, good old angle sum triangle. Angle A equals what's left here at B2. Therefore, the triangles are similar by angle, angle, angle. Now I want BD squared out of it. So I'm going to make sure I have a BD above and a BD below. BD from the green, BD from the red. BD is second, third, so therefore I take second, third from the red. BD is first, third in the red, therefore I need first, third in the green. There it is there. Notice similar triangles proven there. And that gives exactly what I want to prove. Let's look at one more. So we have straight lines, we have a rhombus. Now remember that means that is parallel to this and that is parallel to this, and SP equals PQ equals QR equals SR. Prove that triangle SUR is similar to triangle QRT. That's pretty straightforward because you're told the triangles to prove similar. The equal lines don't come into it. Be careful of the equal lines with similar triangles. That's congruent, and this would be the case because those don't correspond. If you have a look at this one is opposite T, which is equal to R. So for the triangles to be congruent, US would have to equal RQ. But this is not the case. But we have U equal R3. U is equal to R3. Pretty straightforward, corresponding angles, parallel lines. We have R1 equal to T, corresponding angles, parallel lines. And we have S1 equals Q1, good old angle sum triangle. So there we are. There are our similar triangles. Now if we have a look at the second one, straight away I can see I have a problem because PS squared isn't part of this. PS isn't there. So let's go into a thought process. That means PS times PS equals SU times QT. Well, if we did a vertical horizontal, it wouldn't help us. So what we can do instead is we could say, well, PS is equal to other sides. Have a look. PS is equal to other sides. So can we actually do substitutions? There's our proof there. That gives us this here. And in fact, there we are. By rhombus, have a look again. QR is equal to PS and SR is equal to PS. So in my thought process, I say, well, that's the case. I'm asking questions. Will this, I faded this one out, give us what we need to prove? And magic's magic. It will. So therefore, it follows that SU, notice there's our thought process here, SU over PS equals PS over QT. So I'm going to start by SU over QR equals SR over QT in order to be able to get there. So SU over QR, SU first second over QR first second equals SR first third over first third. There it is there. But we have those sides rhombus equal to one another. I don't bother to write of. That's a waste of ink. And writing something like sides of rhombus are equal, oh, that's an essay. That's the whole essay. So now look, I have substituted. Instead of QR, I put PS, because QR and PS are equal. Instead of SR, I put PS, because SR and PS are equal, and that gives me straight what I want to prove. And this sort of thing often happens in similar triangles. You're going to find it's going to come up more in these videos where you need to do substitution. So as soon as a line doesn't fit, you say, hang on, I can't find that in the similar triangles. You say, well, is it equal to anything else within the similar triangles? So we can substitute.